So I'm presenting part two of laminated object manufacturing, or LOM. You can probably remember what the process looked like from last time, but if you can't, this helpful animation will help. There's a paper take-up, there's a paper supply, there's a roller that comes over, applies heat and pressure to the adhesive coating the material layer. Each layer is added to the substrate. Laser cuts the profile of the 2D image, and so it goes on until the material or the part is done. And then there's some decubing or material removal that needs to happen afterwards. Let's watch a video. So this is from the Institute of Technology. And so here's your animated LOM printer. It's tracing the 2D profile with the laser. And again, it can be a knife, doesn't have to be a laser. It's done tracing the profile. It adds the cross hatches where the material is going to be removed. Adds another layer. The roller comes over, applies pressure and heat, sealing the adhesive layers. Next, the laser keeps on cutting. Next profile. Cross hatching is done. Roller comes over, another layer is added, so forth. As that's happening, the platform is moving down and the part is being built. Let's go back here. So, part's almost done. There we go. See, there's a lot of material left over, and you can see where the cross hatches were made. And now that's where those little parts are going to come out, and you're left with your, hopefully, your finished part. Yay! So here's another video, desktop printing, not just, I'll skip through this really fast. So here's a desktop printer. It's $9,000 now. And you can do this sitting around your desk if you have spare $10,000 lying around. It's a good question. As you can see, they built the part. Now they built it, they took it out, and they're decubing it like you saw with that animation earlier. This part looks a little more complex than the other one. And as you can see, you get a lot of characteristics with this. Most of them, if you use paper, you get like wood-like characteristics, so you can sand it down later. And this technology is definitely mostly used for prototyping. Now they're inventing ceramic tape and metal tape, which is really interesting. And basically the tape, because it has the adhesive on there, and they're building new parts. But that's at the very cutting edge. Coming back to our process, some of the most dominant process variables include temperature, so the temperature of the roller, the pressure you're actually applying to that layer as you're adding it, thickness of the layer, as we'll see later, a very key parameter with this process, the chemistry of the adhesive, so how well you're actually applying that and how well it's bonding. Are there any voids being formed? And again, laser parameters, so scanning speed, beam width, things like that. Other important factors: speed of the roller, temperature of the base plate, temperature in the actual chamber where you're making the part, and then orientation angle. Orientation angle is very important, along with layer thickness, to maintain surface finish and surface texture of the finished part. This first research study was done by actually somebody you may know, Dr. Brian Paul, right here. It's called Effective Layer Thickness and Orientation Angle on Surface Roughness in LOM. So the scope of this study was to investigate the source of roughness in this process and hopefully offer insight into controlling the process better. And there was a theoretical model developed based on a previous fabrication process, and this study verified the model with experimental results. Laminated object manufacturing, the biggest application again is making prototypes, and when those prototypes are made for aerospace or automotive industries, there's a lot of flow testing done. So surface characteristics, like I was saying, finish and texture, are really important. And additionally, with this process, you need a lot of secondary involvement as well. So decubing the material, any finishing with sanding, again, because of poor finish, and that involves time and cost, and also limits the type of shapes you can make. I think last time we talked about you can't make hollow shapes, or you can't make huge overhangs and things like that. So surface roughness, as you can see in that image, that's the prototype part they made. It's basically a cube It looks like a pyramid, up facing and down facing, but if you can imagine, they made a cube, and they made it this way so they could have what's called up facing surfaces and down facing surfaces. Now, surface roughness is clarified by what's called the fundamental surface feature, so it's pointed out in magnification over there. So you repeat that fundamental feature and you get a surface profile, and you measure that profile and you can measure surface roughness. So really a measurement of one of those features, you can really get the whole surface roughness. So the model they developed was built around that. The model was originally built for stereolithography, but they modified it based on that feature for LOM. And this work was done in 2001, so a while ago at that. Again, surface roughness comes from the stair-stepping effect, like in all freeform fabrication processes, and this primarily occurs when surface orientation is not orthogonal to the laser beam axis. As you can see, the misorientation angle here is 45 degrees, and that was done intentionally so that they had some roughness to measure. Again, this highest resolution is possible if you can reduce layer thickness during the build cycle as well. So they conducted a full factorial experiment to investigate the effect of layer thickness and therefore this average centerline roughness, which is RA. A key question from their study was, is the orientation angle and paper thickness, are they statistically significant with respect to the centerline average roughness? And yes, they found that definitely both were found to be statistically significant. In addition, the interaction between the angle and the cube side was also found to be significant. So this demonstrates that the profile, that fundamental surface feature, was not actually any type of straight line, it was a parabola. And that's actually the source of significant variation in roughness. That's what changed between the up-facing and the down-facing. And the model was poor predicting the roughness with the thickest layer height, and it was found that the average percent error is approximately negative 13%. So the model tends to overestimate surface roughness, and this is probably due to handling or the type of features that get compressed when you're measuring these things. Then again, both are found to be statistically significant. Another question was, can the model be developed to accurately predict? And it was found that the model could accurately predict. As you see on the figure on the right, that's in that box. The figure on the left is actually their measurements using 2 profilometers, if that's how you say it, and the image to the right is actually their simulated or based on their model. And you can see that the model is actually smoother, so the measurements tend to be a little bit rougher, but it was pretty accurate. The absolute percent error was actually only 26%. So yes, a theoretical model was developed, and it's actually pretty good at measuring surface roughness. So now let's look at another study. This study is new approach of online waste removal process for laminated object manufacturing. I'd mentioned that waste removal or waste itself in this process is a big issue, and it also adds time and cost, which is not very good. So these researchers developed a new process, hopefully, that you could make hollow parts, make all these shapes, and reduce the time required by actually removing that waste during the process itself. So you can see the different components of that process listed below that figure, but basically what's happening is that everything happens the same way as described before, but the adhesive is actually upward facing, it's not down. So when you remove that number 6, when you remove that layer, you're actually removing the wasted material, and you can go back over, feed it over again, and recover that. So that was the scope of their study, and then they conducted a simulation to prove that this was in fact feasible. So can this new process be developed? Well, they used the 3D model, as you can see on the left. They made some type of a gourd or instrument, and they made this ball inside of a cube. Now, the images stacked on top of another to the right of that were made using the traditional LOM process, so none of this online waste removal. The images next to that were made using the new process. And as you can see, you can actually make shapes like that ball inside the cube, and you can actually make a finer surface finish for something like a gourd. And the gourd actually is hollow on the inside. The first process couldn't do that, but the second process could. So this new system is feasible, and it can decube the material online. Now, does it compare to traditional, and is it feasible, and does it perform better? So compare traditional, or compare, I'm sorry, on the traditional LOM to the proposed process. First, for the amount of the waste removed online, and for time to decube. As you can see before, you can't remove any waste material online. However, the proposed process removes about 30 to 80%. Here it's shown 50% for that first that gourd-shaped piece, and the other was about 80%. And then the process time drastically improved from 80 minutes to 15 minutes, and from actually not being able to do it at all to 10 minutes only. Then again, the characteristics of our proposed process, the adhesive is upward. It's a self-adhesive, and again, laser power is less consumed because you're not spend time cross-hatching any of that part you'd remove earlier. You're already removing it during the process. You can make hollow parts. Post-processing is short and easy, so costs are reduced. And the strength is good, apparently. There was not really much discussion about that, and there's no damage done to the part as well. So a design model, there wasn't an exact design model out there, but I felt that a model which was able to predict surface roughness, which is actually, this is from Dr. Paul's paper, that first paper I presented. And what this does is that this is based on a model for stereolithography by adapting penetration depth of the paper and the ablation energy of the paper itself. They adapted this model to work for LOM. And by using the ASTM standard for surface roughness, doing some numerical integration, you can actually fine-tune your working parameters for your laser, because some of the components of the laser are working distance and the optics itself to get a better resolution. And so you could do this with this model, and I think this would be a good way if you're using LOM to fine-tune your process, because surface roughness is the most critical dimension, as we saw. Some other models out there, though, some thermomechanical models, were published in 1998 and 1997. So as you can see, this process has been around for a long time, but they're still coming up with new innovation. And these are my references.